Hi, this is problem 2.25. It tells us that a gas in a piston cylinder assembly undergo a process for which the relationship between pressure and volume is PV squared equal constant. So this is a polytropic process. So PV equal constant used to find work in a variable pressure system. When pressure varies during a process, we call it a polytropic process. The initial pressure is 1 bar. The initial volume is 0.1 meter cube. And the final pressure is 9 bar. Determine the final volume in meter cube, in cubic meter, and the work for the process in kilojoules. So let's write down what is given to us. So the initial pressure is 1 bar. The final pressure is 9 bar. Makes sense. So here we increased the pressure. So what does that mean? That means that this process is a compression process. So that means we start at point 1 and we are asked to find the final. So the final should be more than point 1 or less than point 1. We are compressing it, so that means it should be less than 0.1. So now we are asked to find the work from the initial equilibrium state where the pressure is 1 bar and the volume is 0.1 to the second final state, the second equilibrium state where the pressure is 9 bar and we need to find the final volume, but we know because it is compression the final volume will be less than 0.1 meter cube. So now we can, so we wrote down what is given to us. Now let's illustrate what is given to us. So we can see what we have and what we need to find visually. So here we have a graph. The vertical is pressure and the horizontal is volume. So here we start with our initial state, and then we have our final state or final equilibrium state right here. So now we will connect between these 2 points and we call this line the path. So as you can see, we go from initial to final. So we're going toward this direction. So toward the left. So when we go toward the left, it means that we're going to have negative work. So here at initial state, we start at 1 bar and the final state is 9 bar. We start at 0.1 and we need to find the final volume. So here we can, another illustration where we drew the piston cylinder assembly, and here we have the gas, and this dashed orange line represent the boundary. So this gas is our system in here, and the pressure initial is 1 and pressure initial is 0.1. So next what we did is we compressed the gas. The pressure increased to 9 bar and we are asked to find the final volume in here. And this system, we call it closed system because there is no change in mass. We are asked to find the work, and the work is the area under the curve or the area under the path. So that tells us that work depends on the path it takes to go from initial state to final state. So here, this is called a polytropic process. 2, we call it the polytropic index. Now, because the pressure times volume to the power 2 equal constant, that means that the initial pressure times the initial volume squared, that product equal to the pressure final times volume final squared. All right, so now we want to find the the final volume by using this expression. So right here, let's solve. So we have the initial pressure, we have the initial volume, we have the final pressure. We can solve for the final volume. So we will take the pressure final to the other side of the equation. And now we can get rid of the square by taking the square root of both sides. And now we can plug in the values that, so pressure initial over, or we can rewrite it as pressure initial over pressure final times the initial volume squared. Now we can plug in the values. So pressure initial is 1 bar. Then we increase the pressure and it becomes 9 bar because it's compression, times the initial volume is 0.1 meter cube to the power 2. Now here the bar will cancel with the bar, and here the 2 will cancel with the square root, because 2 to the power 1/2, by using exponent rules, 2 to the power 1/2 is 2 times 1/2, which will be 1. So right here we will write our volume. Final volume will be 0.033 meter cube. All right, so now we were able to find the final volume. Next, we want to find the work that it takes, or the amount of energy it takes to compress this gas. So what is work? To find the work from the initial state to final state, it will be pressure times the change in volume. And in the previous slide, we mentioned that the work is the area under the path or under the curve. So that tells us that we need to sum the areas or take the integral. And right here, we have this pressure in here. So let's rewrite this integral in a general form. And that's what I will show you. PV squared equal to constant. So what we will do in here is we will solve for the pressure. And that by taking the volume to the other side of the equation from multiplication to division. So the pressure will equal to the constant divided by V to the power n. Why didn't I write V to the power 2? We can. But what I want to do in here is I want to find a general expression when we are given a polytropic process with other than a polytropic index other than 2. Let's say we have 1.3 or 1.5 or 2 or 6 or 5. We want to be able to to plug in the value without doing the integral every time for different polytropic indexes. So that's why I replaced 2 with n. And here what we will do is we will plug in the b value back to this integral. So the work from the initial to final state will be the integral from initial volume to final volume, and the pressure we said it will be the constant divided by v to the power n dv. Now we will take the constant outside the integral, and it will be from v initial to v final, and it will be v to the power minus n dv. So now we will use the integral rules and to solve for this. So that will be n plus 1 divided by minus n plus 1. So that's what we're going to have in here from the initial all the way to final. Now we will rewrite this. So here we will have common denominator. So that will be our final, V final minus n plus 1 minus V initial to the power minus n plus 1. And here we can rewrite it as 1 minus n. So now let's take a look at this constant. So we said that constant right here, when we can solve for it, so it will be b p to the power v to the power n. And the constant will distribute it into this parentheses. So we will have the work initial equal to, so C for it will be B final, V final to the power n times this one, V final to the power minus n plus 1 minus B initial, V initial to the power n. So that's C right here times V sub I to the power minus n plus 1. So what we will do in here is that we will use the exponent rules. Now we will use the product rule for exponents. So a to the power m times a to the power n equal to a m plus n. So here it will be n plus minus n plus 1. So n minus n will be 0. So it will be you will be left with v final to the power 1. All right, so this is our expression that we can use for any polytropic index. But pay attention, we cannot use if the polytropic index is 1, because 1 minus 1 is 0, and that will give us an error. So this expression can work for all polytropic indexes except 1. So if for other or future problems, and instead of going through the integration for every polytropic index, this will be our general work equation. But for polytropic index number 1, it doesn't work. All right. So now this is the expression that we got, and now let's plug in the values that we are given and found. So the final pressure, we will convert 9 bars to Pascal. So it will be 9 times 10 to the power 5 Pascal. The final volume, we found it to be 0.033 meter cube minus initial pressure is 1 bar, so 1 times 10 to the power 5 Pascal, times the initial volume is 0.1 meter cube, divided by 1 minus 2. So that will give us what? It should give us negative answer, and it does give us a negative answer, minus 19700 joules. But we are asked to find in kilojoules, so it will be, so we will divide this by 1,000, it will give us 19.7 kilojoules. And that is the answer for B. Next problem is 2.26. It tells us that we have a carbon dioxide, CO2 gas, within a piston cylinder assembly, undergoes an expansion from a state where P sub 1, or state pressure at state 1, equal 20 pound-force per inch squared, and volume at state 1 is 0.5 feet cube, to a state where pressure at state 2 is 5 pound-force per inch squared. So here we decrease the pressure. So that means this is expansion. And the volume at state 2 is 2.5 feet cube. The relationship between pressure and volume during the process is P equal A plus BV, where A and B are constants. We are asked for the carbon dioxide, evaluate the work in feet times pound force and PTU, and we are asked to evaluate A in pound force inch squared and B in pound force per inch squared per feet cube. So let's write down what is given. So pressure 1 is 20 pound force per inch squared. Pressure 2 is 5 pound force per inch squared. So this is expansion. And volume 1 is 0.5 feet cube. And volume 2 is 2.5 feet cube. So volume increase. And we are asked to find the work from state 1 to state 2 in foot times pound force and PTU. Now, also, we are asked to find the A value, which is the process relationship, the A and B, these two constants. Now, it is a good practice to read the problem very well, to write down what is given, and for a practice for you, just like what we did in the first problem, 2.25, you can sketch this problem and draw the piston cylinder assembly to illustrate and demonstrate what you are given and what you need to find. This is a good practice, and as an engineer, one of the skills that you need to develop is to know how to tackle different problems. So by reading the problem properly, writing down what is given, what you need to find, and use sketches to illustrate, or drawings to illustrate, or graphs to illustrate, helps you understand the problem way much better. So right here, what we want to do is we want to find the A and the B value. So how will we do that? So we said that at state 1, pressure 1 equal to A plus B equal V1. So the pressure 1 is 20 pound force over inch squared, and A is equal to B times 0.5 feet cube, and volume. So we replace the given volume and we replace the given pressure and given volume. Now at state 2, we have pressure 2 equal A times B V sub 2. The pressure 2 is 5 and the V is 2 and V sub 2 is 2.5. Now what we want to do is we want to solve for A. So we will take this to the other side of the equation. It will be minus B 0.5 feet cube plus 20 pound force over inch squared equal to A. Now let's plug in A into the equation at state 2. So A, we will replace it with minus 0.5 B feet cube plus 20 pound force per inch squared plus 2.5 B feet cube. All right. So now we have this minus 0.5 B and plus 2.5 B. So we will add these two, and it will give us 2B feet cube plus 20 pound force per inch squared. So now we will move 20 to the other side of the equation to solve for B. So to look at minus 20 pound force per inch squared plus 5. They have the same units, equal to 2B. So now we can solve for this. It will be minus 15 pound force because to B. So now we can solve for B by dividing minus 15 divided by 2. It will be minus 7.5. And here's the pound force per inch squared right here. And the feet cube, we take it to the other side of the equation by division. So this is the unit for B. Now what we will do is we will plug B to one of these two state equations. Let's plug it at state 1 in here. So this feet cube will cancel with this feet cube. And we can write this, so that will be A times minus 7.5 times 0.5 is minus 3.75. Now we can easily solve for A. So A will be 23.75 pound force per inch squared. So here we were able to find or able to evaluate A and B. And this is the answer for B. So now we can use this pressure to solve for work. So again, work from state 1 to state 2 is pressure times change in volume. Now, what is pressure? Pressure from the problem, we are told that pressure is equal to, and by evaluating the two constants, this is the pressure expression as a function of volume. Now, since we have a variable pressure, we will use integration. So pressure from 1 to 2, it will be from initial volume or volume at 1 all the way to volume at 2. And it will be pressure, which is this expression right here, times dV. Now, here we will solve for the integral. So it will be 23.75 V minus 77.5 V squared, because V squared 7.5 divided by 2 it will give you 3.75. So here we will plug in the values that we need, the V squared and the V1. So now because the 23.75 is given, we found it in inch, and we are asked to find things in feet. So before we proceed, it's a good idea to convert the 23.75 and the 3.75 from inches to feet, and that's what we did in here. And to convert the 3.75, we will also use the same conversion factor, which is 144 inch squared is equivalent to 1 feet cube squared, I mean. All right, so now we will plug in these new values, which is, instead of 23.75, it will be 3420 pound force over feet squared times 2.5 feet cube minus the 3.75, we change it to 540 from inch to feet, pound force feet to the power 5. And the same thing for the other term in here. All right, so now let's take a look at this. So here the feet squared will cancel with feet cube, and we will remain with 1 feet. So this term will be what? Pound force times feet. Good. That's the unit that we want to find. And making sure before you proceed that you got the right unit, it tells you that you are in the right path. All right, what about here. So this is 3 and 2. From exponents rules, 3 times 2 is 6. So phi to the power 5 will cancel with phi to the power 6, and you will remain with 1 feet. And here you will get pound force times feet. So for each term, we're going to get pound force times feet, which is the unit that we are looking for. So when you plug this into your calculator, it will give you 3,600 pound force times feet. That's good. We are also asked to find in PTU. So here we will use a conversion factor. So we will say that 3,600 pound force times feet times 1 British thermal unit is equivalent to 778 pound force per feet. So these pound force per feet will cancel, and we can get the work done, or the energy needed to compress the gas is 4.63 PTU. This is the answer for A. Next problem is 2.27. It tells us that a gas in a piston cylinder assembly undergo a compression process for which the relationship between pressure and volume is given by BV to the power n equal constant. The initial volume is 0.1 meter cube. The final volume is 0.04 meter cube. And the final pressure is 2 bar. Determine the initial pressure in bar and the work for the process in kilojoules. If n equals 0, n equal 1, and n equal 1.3. So here we are told that the relationship between pressure and volume is a polytropic relationship, or a polytropic process. Now, so let's write down what is given. So initial pressure, that's what we are asked to find. Now, for the initial volume is 0.1 meter cube. And remember, from this state, we compressed the gas. So this is compression process. So that means the final pressure will increase 2 bar, but the final volume will decrease, which is 0.04 meter cube. Here we are asked to find the work from initial to final state in kilojoules, and here for each one of these polytropic index. Polytropic index n equals 0, n equal 1, n equal 1.3. All right, so now remember from the first problem, BV to the power n equal constant. It means that the initial, or the first state, is pressure times volume product is the same as the final or second state. And that's what we have in here. So now for A, when n equals 0, we will say pressure initial V to the power 0 equal to pressure final V final to the power 0. So anything to the power 0 is 1. So that will give you what? Pressure initial equal to pressure final. So that tells us that pressure initial is 2 bar. So this is called an isobaric compression process. It means it have a constant pressure. Since we have a constant pressure, not a variable pressure, that will be simple. You know, pressure is constant, is not changing. So it will be 2 times 10 to the power 5 Pascal times the change in volume. The change in volume is 0.04 meter cube minus 0.1 meter cube. Plug this into your calculator, it will give you minus 12,000 joules. And we want it in kilojoules. We divide it by 1,000, minus 12 kilojoules. Now for C is 1.3. Now, why did I jump to C? Now remember what we mentioned in the first problem is we found a work expression for any polytropic index except one. So this is because we already know it. So let's use this expression and find the C value. So right here, this expression right here, we can use it to find the initial volume when the polytropic index is 1.3. So now we can plug in the values that we have to find the initial pressure. So then initial pressure is 0.608 bar. And from what we found from the first problem, 2-25, this is the work expression that we got. So now we can plug in the values that we have and the values that we found. And this will give us a work of -6400 joules, or we divided by 1000, which will be -6.4 kilojoules. Now for B, when n equal 1, now B1, so now we can solve for P initial, and we can plug in the values that we have to find B initial. So B initial is 0.8 bar. Work from initial to final is equal to pressure times change in volume. So what we will do is remember that BV to the power 1 is equal constant. And that we can solve for B, which will be C divided by V, taking V to the other side of the equation from multiplication to division. And remember, since this is constant, B initial, V initial equal to B final, V final equal constant. So now we know that work is the area under the path or under the curve, which will be pressure times change in volume. We will replace the pressure with this expression, which is C over V, dV. Now we will take C outside the integral, and it will be 1 over V dV from the limits V initial, V to V final. Then we will take the C out, and we will use the integration rule. 1 over V, it will be 1 ln V, or log V. So we will solve for this further. So it will be ln V final minus ln V initial, and by knowing logarithmic rules, we can rewrite this and become C equal to ln V final over V initial. And so here we have a constant. A constant can be any of these two. So here I wrote the pressure initial, volume initial, ln V final over V initial.